Excellent. Hello, everyone. Thank you for coming to the second Quantum Engineering Graduate Association seminar. Today, it's my great pleasure to introduce Professor William Oliver from MIT. Professor Oliver has joint appointments in the departments of electrical engineering and computer science and physics at MIT, and is also a fellow at the Lincoln Laboratory, MIT Lincoln Labs. Along with that, he also serves in several leadership in several leadership positions, including being the director of the Center for Quantum Engineering, and as an associate director of the research lab for electronics at MIT. Along with that, he also has won several awards, and recognitions, including being a fellow of the APS, a senior member of the IEEE, and he's also the Thornton Faculty Research and Innovation Fellow. Professor Oliver's group and work leads the field of quantum engineering, is a leading group in the field of quantum engineering hardware based on superconducting devices, really working across the stack, developing new quantum control protocols all the way down to engineering, understanding, improving the material quality of qubits that go into these quantum computing systems. Other than that, Professor Oliver earned his PhD from Stanford University in electrical engineering in 2003, and earned his bachelor's from the University of Rochester. I'm really excited to hear his talk today, and I hope everyone hears as well, which will be on the giant artificial atoms and waveguide quantum electrodynamics. And with that, I'll hand it off to Professor Oliver. Thank you so much.
Yeah, thank you for that kind introduction, Nima, and also thank you for the invitation to speak here today. I'm really honored to be here, and look forward to talking with you about this topic, which is some work we've done over the last couple of years. And as I'll explain, we're thinking about, how do we build quantum interconnects that can connect different modules or even different chips together. And so it's part of a story that we'll get into. Let's see, there we go. So when we think about atoms, when we say the word atoms, we usually are talking about what you might call small atoms, and small in the sense that the atom itself is much smaller than the wavelength of the light we use to drive it. Okay, so we just call it an atom, but we could also call it a small atom. And because of this, the polarization of the atom follows the wave that's driving it. And as a result, we can think of this polarization in a dipole approximation. And this looks like, or we could represent it as a qubit coupled to a waveguide that's driving it at one point. Okay. So we associate the dipole approximation with a point-like atom. And so if we look at many of the atoms, that people have experimented with, this is generally true. So if we think of natural light or a natural atom with optical light, okay, the radius of the atom's, an angstrom. The wavelength of the light we use to drive it generally is micron or even 100 nanometers. And so the ratio of these two numbers is 10 to minus 3, 10 to minus 4. Okay, so that's pretty small. If we look at Rydberg atoms and microwave light, you can see the radius and the wavelengths here, and that ratio is in fact even smaller in this case, okay? And if we think of artificial atoms like conventional transmons, it's a type of superconducting qubit in microwave light, this ratio is still 10 to the minus 2, 10 to the minus 3. So we're definitely in the small atom regime. But that need not be so. And it need not be so because we can build and manufacture superconducting qubits, and we could attach them at multiple places along a waveguide such that the separation between those connections are on the order or maybe even larger than the wavelength. And in this case, the dipole approximation is no longer valid because we need to consider quantum interference between these different points. And you could, schematically represent that as a qubit connected at discrete, well-separated locations, right? And now we need to think about this interference that occurs between these points, x1 and x2. Okay, so natural atoms, of course, we represent on the Mendeleev table, and we think of these atoms as being built from constituent elements like protons, neutrons, and electrons. And artificial atoms that we build from superconducting materials, the constituent pieces are basically electrical devices like inductors, capacitors, and Josephson junctions. And with these, you can create a large number of what we call artificial atoms. As I'll show, they'll behave like atoms in some ways. And you might even think of this as, a sort of Mendeleev table of artificial atoms. And so these artificial atoms, of course, they're much larger than these natural atoms. They're huge. But they can be designed with custom parameters depending on how many junctions and how many capacitors and how many inductors and the value, et cetera. So let's look at the simplest one. And in fact, before we look at the qubit, we can think of just a harmonic oscillator. It's an LC circuit. It's a resonator, parallel resonance circuit. And because it's a harmonic oscillator, the potential profile goes as, in this case, phi squared, where phi is the reduced flux, this parabolic potential. And if we cool this electrical circuit down to a low temperature, where low means that the energy scale kT is much smaller than this energy scale, which is Planck's constant times the resonance frequency of this circuit, then this is a quantum circuit. And it'll have discrete energy levels that we can label 0, 1, 2, et cetera. But the one feature is that the energy that you would use, or the frequency you would use to drive the 0-1 transition, is degenerate with the 1-2, with the 1-2-3, and the 3-4, et cetera. So there's no way here to uniquely define the 0-1 transition because it's a harmonic oscillator. So we'd like to introduce a nonlinear element to make it anharmonic, and the element we use is called a Josephson junction, which is a tunnel junction made from two superconducting leads, typically aluminum, doesn't have to be, but aluminum is convenient. And the insulator is aluminum oxide, about 1 nanometer thick. This is the circuit's diagram. And Brian Josephson introduced the current and the voltage relation for how current flows through a tunnel junction like this and how it generates voltage. And I won't go into detail on that, but as electrical engineers, we know how to combine current and voltage together to define an inductance. And the inductance that this device features is highly nonlinear in the current that goes through it. So its value of inductance depends on the current that's going through it, and therefore it is a nonlinear element. We can further calculate the energy of this circuit, integrating I times V, and see that the potential energy goes as a cosine. So it's an anharmonic potential. So the way I think of a transmon is that I replace my inductor here with a Josephson junction, nonlinear inductance now. It's an anharmonic oscillator. The potential profile is no longer quadratic, but it's now a cosine potential. And one consequence of that is that the 0-1 transition frequency is no longer degenerate with 1-2 or the rest of the ladder. And so I can uniquely define and address the 0-1 transition, and we'll just draw a box around this and call that our qubit. So as I mentioned, many artificial atoms can be built from this concept just by choosing values of these parameters, as well as the number of junctions, the ratio of their areas, et cetera. But we're going to use a transmon in this work. And one feature of it is that we can tune that 0-1 transition frequency in situ. And the way that we do that is by taking a junction and splitting it into two junctions in a loop. And if we put a magnetic field through that loop, what we see is that we can change what's called the Josephson energy, or the effective critical current of that object, as a function of the magnetic flux bias that's threading the loop. So it takes its maximum value at 0 flux and its minimum value at plus or minus half a quantum unit of flux. So the upshot here is that we can tune our qubits by taking this junction, splitting it into a squid, and then applying a magnetic field here. And now this 0-1 transition frequency is tunable, which is quite a useful feature. And just to show an example of what that is, the 0-1 transition frequency is given by this formula here, where EJ is a Josephson energy, EC is a charging energy. These are defined quantities. Their values for this qubit are shown here. But the upshot is that the frequency of that 0-1 transition is tunable, right, by the magnetic field I apply to this loop. Okay, so we will use tunable transbond qubits in this work. So we typically, you see here, we typically chosen the frequency. We get to choose this frequency, but we choose it to be in the few gigahertz regime, and that's because we have access to, really great microwave equipment that operates in that regime, largely driven by, well, originally radar and gallium arsenide and the development of 3.5s and 2.6s in the 80s and 90s, but also by the fact that we have cell phones today and they all operate in 2 to 5 gigahertz range. Now, 5 gigahertz, if you say what's the equivalent temperature for that in terms of thermal energy KT, that T would be 250 millikelvin, which means that if my qubit sits at 250 millikelvin, just thermal photons from the environment will drive the 0-1 transition. Okay, so we want to be operating much lower than that because we don't want thermal photons driving transitions. We want, our intentional pulses, our control to do it. So we operate these devices in what's called a dilution refrigerator. The pictures are shown here, and they operate at or below 20 millikelvin. Now, 30, 40 years ago, this was the research project of many PhD students, but today, these are commercially available. To give a size scale, the diameter here is about 0.5 meter, the depth's about 0.5 meter. And you can see lots of familiar pieces, I think, in here, including microwave switches, coax cables, attenuators, and inside these packages that you see here are the chips that hold the qubits or resonators that we're testing. Okay. Now, we manufacture these, and I want to emphasize that superconducting qubits can be, or typically are grown on and patterned and defined on silicon wafers. Can also use sapphire, but we use silicon. And it does so, with the tool set that you would find in a modern silicon foundry. So superconducting qubits are absolutely a silicon technology. And what I'm showing here on the lower left is a 200 millimeter wafer with lots of qubits on it, many, many designs here. If we zoom in on one of them, you can see 5 qubits lined up in a row. These plus signs are capacitors, actually. To the upper right are readout resonators, and to the lower left are control lines. And if we zoom in further, here's that capacitor. It's a capacitance to ground. It's not a parallel plate, it's a lateral capacitor. And so that's the C of the LC circuit. The L is tiny, it's here. So if we zoom in on that, you can see there's the loop. It's got 2 Josephson junctions, and this loop is where we apply a magnetic field to tune the 0-1 frequency. And then over here, we see a single junction. And so this is one electrode, this is the other electrode, and aluminum oxide in between. This is aluminum. Up here, I'm showing, air bridges and crossovers, which allow us to break the plane. At the end of the talk, time permitting, I'll go through and show some of the work we're doing on bona fide 3D integration at that time. So I mentioned that we use microwaves to control these devices, or maybe more appropriately, RF. And this is done through standard IQ mixing. IQ means in phase, Q means quadrature. And this mixer basically multiplies together a local oscillator signal that comes in the LO port times this signal coming from an arbitrary waveform generator. And we choose whether we apply it to the I port or the Q port. And then what comes out is the multiplication of those two, which is this pulsed microwave at the sum or difference frequency. And we can choose single sideband and do things to just look at one of those frequencies with filtering. But the reason I mention this is because if we choose the in phase port of the mixer, then the phase comes out without shifting, or let's call that 0. And we're going to associate that with the x-axis of a Bloch sphere. And if we choose the Q port, then there's a 90-degree phase shift, and we'll associate that with the y-axis. So what we're seeing here is a video where it's a simulation, of course. What we're seeing on the left here is the Bloch sphere, or planet Earth, if you want to think of it that way. The blue vector is the Bloch vector, or the state of the qubit, and the red vector corresponds to this envelope of the pulse we're applying. Now, what you see is now an X pulse. We're using the in-phase port. Here's minus X. We'll now switch to the quadrature port, and so now we're rotating around the y-axis. And you can see with half of the area, we now do half, a pi/2 pulse, go to the equator, and then another pi/2 pulse brings us back to the North Pole. So this is the way that we can control the qubit and its position on the Bloch sphere using standard IQ mixing. Okay. One remarkable feature of superconducting qubits is that their coherence times have improved tremendously over the past 20 years or so. And this is due to a combination of materials improvements, fabrication improvements, and of course, design improvements. Now at MIT and Lincoln Lab, we don't have a favorite qubit. We look at many different types of artificial atoms. Here are some typical times that we're getting for those qubits. And what I show here in the lower right are review papers. If you'd like to learn more about qubits or materials, et cetera, please take a look here. You might ask, does this trend continue on forever? Well, probably not forever, but how far will it go? And we've done some work there, which I won't be able to talk about today, but one source of error that we are going to have to deal with is ionizing radiation. And so there are a couple of works that have been done now. This is ours here, that looks at ionizing radiation either from radionuclides in the concrete of our laboratories or other materials, as well as cosmic rays or muons they generate from outer space. And these get absorbed into the substrate and can create quasi-particles, and quasi-particles are a decoherence mechanism. Okay, so I won't have a chance to talk about it, but that's the next target. Currently, we believe that's going to limit us to a few milliseconds if you average it over a long time for T1. Also, improving the quality of our control in our 2-qubit gates is very important. And I just mentioned that we have work where we've demonstrated almost 99.9% 2-qubit gates with the I-swap and the controlled Z type using tunable couplers. And again, I won't have time to talk about it, but here are some references here in case you'd like to read about that. But what I'd like to talk about today is waveguide QED, quantum electrodynamics, and giant artificial atoms. I'll start there. We'll talk about directional photon emission. And then at the end, again, time permitting, I'd like to talk about some lattices that we're building and the need for 3D integration as we go forward. So before we get into waveguide QED, it's worthwhile to talk about cavity QED. So cavity QED, or cavity quantum electrodynamics, is the dominant architecture today for superconducting quantum information processing. And in fact, it's dominant in other fields as well. And the idea is that if we put an atom in a cavity, that the atom will interact with the cavity field, and with a coupling strength G, it can exchange energy with that field if the atom is resonant with the cavity. And that leads to an enhancement of spontaneous emission. And in fact, that's something that we don't want. So generally what we do is we detune our qubit from the cavity field, and now that acts to protect the qubit. And the reason is that this atom, of course, in free space has a quasi-continuum of modes that it could emit to, but inside this cavity, the cavity creates a discrete set of modes separated by the resonance frequency, right? And if you sit in that cavity detuned from those modes, then basically you could think of it that you can't really emit. Okay, that's not entirely true. There's a little bit of a chance, but it's highly suppressed. Okay, so that's quite useful. It's a way to protect the qubit. Now, of course, the qubit still has other modes that it can emit to, like say defects in the substrate, for example. So there is what you might call a non-radiative emission, and we'll call that gamma. And then, of course, the fields inside the cavity can leave, and they do that with a rate kappa. Okay. So this is, by choosing G to be very large compared with kappa and gamma, we can be in the dispersive strong coupling regime, and that's how we can control the qubits and read it out while also having protection. Okay, so that's really good. But what we want to do is today talk about waveguide QED. And in some sense, this is a really bad idea, right? Because we just lost the protection of the cavity. So why would we want to do this? Well, one reason would be that if we want to connect qubits to each other, it's much better to do that using an open waveguide because we don't have those cavity mirrors blocking us. Remember, we wanted the leak rate out of the cavity to be quite small. And we don't have that here. So it's good for quantum interconnect. It's also good for studying some physics like dissipative phenomenon, quantum simulations of open systems. And, but as I said, the engineering motivation to me is quantum interconnects. Okay, so the challenges are that the dissipation is always on. If you couple a qubit to a waveguide, there are lots of modes it can emit to, and it's a quasi-continuum. So there's no way to detune from any of those modes. Okay, and the second thing is, how do I engineer interaction between qubits along the waveguide? Okay, it happens, and we want to engineer that, and we'll talk about that today. So this is what it looks like. We have qubits, they'll be superconducting qubits, coupled to a waveguide. It'll be a coplanar waveguide. We'll see a picture. And you can think of it as in this way. There's a 50 ohm waveguide, and the qubits are capacitively coupled. And here's our transmon qubit with its squid, so we can tune its frequency. It's flux tunable. And this is what it looks like. Okay, we have our waveguide here. It's a coplanar waveguide. The dark region here is aluminum, and the white region is the field below it, the silicon field. Here's our qubit. This is one plate of the capacitor. Here's ground. Here's the line that comes in to do the flux biasing. Here's a zoom in of that. So we drive current and, mutually couples in some magnetic field. And then this is how we drive the qubit capacitively, right? So voltage driving. That's how we do the microwave or RF drive. Okay. So let's think about coupling atoms to propagating photons. And we'll start with just a natural atom in free space, 3D space. So here's your qubit. We apply a plane wave field to it, and that induces a transition from the ground to the excited state. Okay, that's straightforward. So there's a small scattering cross-section, a small overlap. And there's also poor spatial mode matching because when that atom relaxes, it doesn't emit a plane wave, it emits a spherical wave. Okay, so we would say that this is a poor spatial matching, mode matching. Now in a 1D waveguide, you can drive the qubit that's coupled to it to its excited state. And the coupling strength here between the two is gamma. And then when it relaxes, it's going to emit a photon, and it's going to either go left or right. Well, it's going to go both left and right, right? That's the way this works, right? Because it's 1D. So we've confined the light matter interaction to 1D. One other advantage is if you look over here, there's quite an array of quantum interference, and the pattern is quite complicated in 3D. But in 1D, if you're in the low photon limit, much less than 1 photon on average, the excitation and relaxation of this atom has complete destructive interference, ideally, in the forward direction, and a complete constructive interference in the reflected direction. So it's a very good, it allows us to engineer this in a straightforward way to go to 1D. Now, we need to remember that we have non-radiative relaxation, so that's an important detail. And basically the cooperativity of this is based on, generally, you would think cavity enhancement times an electromagnetic field overlap, but again, we don't have the cavity here. So it's really about electromagnetic field overlap. But we can create very strong coupling between these artificial atoms and the waveguide. And that's an advantage of these giant, or in this case, just superconducting qubits. Okay, so we want this coupling between the qubit and the waveguide. We want that rate gamma to be much, much larger than any non-radiative relaxation. Otherwise, this effect doesn't work. But we can do that straightforwardly. So if we do that and we do spectroscopy, this is what the experiment looks like. We have a network analyzer. It outputs a signal in this direction. Okay, we have some attenuation, and then it comes into our chip. That signal goes on the waveguide. Okay, at this point, it couples to the qubit, and it keeps going. And then we have an amplifier, which gives us back that 100 dB, and then it goes to the network analyzer. And remember, if we have on average much less than one photon coming in, then this interference effect that I described is what we should see. And indeed, that is exactly what we see when we're on resonance with the qubit. So we're going to define delta as the difference between the network analyzer probe field frequency and the qubit frequency. And then we're going to look for how much gets back to the network analyzer. And when we're detuned from the qubit frequency, most of it gets back. But when our network analyzer gets on resonance with the qubit, the amount that goes to the output, drops dramatically, less than 10 to the -4 here. Okay, so this really works very, very well. And we can look at that in 2D. So not only are we now scanning the probe detuning, but we're also looking at the probe power. Remember, the power goes as the number of photons that we're sending. And so down at these low powers, we're basically much less than a single photon. But at some point, the power increases to the point where we're now sending many photons. And the intuition here is that you see that now we're getting field that continues through, and that's because one of the photons is involved in driving this qubit, but all of the other n-1 photons, they just keep going, right? Okay, so that's why this effect requires, on average, much less than one photon. If we take a slice, you can see that effect as a function of the power, how much is getting back to the network analyzer. And you see basically none of it when the destructive interference is perfect. And then, of course, gradually, as we increase the number of photons that are going through the waveguide, eventually it goes up. Okay, so this is spectroscopy of a single qubit probed using a waveguide. So we can think about actually making a measurement. And in this case, we're not using a waveguide. We're using, we're not using our network analyzer, but something else. And basically, we do digital demodulation. But the important part here is what state the qubit's in and how we measure it. So we can put the qubit in a state, let's say X, along the X-axis. And so that's 0 + 1 over square root of 2. And what we'll see when we make a measurement at room temperature, temporal measurement, is that this oscillates back and forth. And that's because this has a known phase, and this phase rotates in time at the qubit frequency. Now, if we had instead put this at the excited state of the qubit, that's a Fock state, and we know that a Fock state has no particular phase, right? Okay, you might say there's some overall phase, but we know that that doesn't matter in quantum mechanics. And so as a result, when we do our averaging at room temperature, because the phase is randomized, we average to 0. So what's interesting here is we don't measure in the qubit ground and excited state basis. We measure in the +x -x basis, right? And when we do that, we record a signal at room temperature, and we apply a weighting function or a windowing function to it. And we look at the frequency, we take that out, and basically that's what gives us a static number or DC number. That's how we do it. And of course, what we have emitted at the waveguide is something like a photon level of energy. And of course, we have to give a lot of amplification to that to get what we measure. So what we measure, S, needs to be translated back and accounting for all of the system effects of loss and gain and filtering and all that. And we can quantify that as an effective added noise. And so we have to account for that as well. I won't go into detail on how we do that, but just you can imagine that that's what we have to do. We measure something at room temperature, and we need to go back and infer what the state was at the qubits. Okay, and you can learn more about this in these 2 papers by Eichler et al. Okay, so waveguide mediated interactions look like this. So we can take a qubit, take 2 qubits, qubit A and qubit B, and we put them on the waveguide, and we separate them by a wavelength lambda. Okay, what is that wavelength? Well, these qubits, we have them at the same frequency, and if that qubit emitted a photon to the waveguide, the photon at that frequency has a wavelength. That's what the wavelength is. And so we separate the 2 qubits by that amount. So when they emit their photon to the waveguide, we would call this a real photon. It's not a virtual photon, it's a real one, and it's called qubit decay, and it happens at the rate gamma that the qubit is coupled to the waveguide. But there are also what you might call virtual photons, where the photon is emitted and then, say, reabsorbed somewhere else. And those can happen off resonance, right? When omega is not equal to omega q. And this is related to what you might call an exchange interaction. So what I want to emphasize here is that for this separation of lambda, there's a destructive interference between red detuned and blue detuned virtual photons. And the way that you can think about that is, let's take a pair that are exactly detuned by the same amount. One is, plus delta k, and the other is minus delta k, right? That's a pair of photon modes that are plus and minus detuned. So they come in with a plus or minus detuning. Their coupling strengths are the same. And so the net effect of the coupling between the qubits is G1 times G2 over this detuning. And you see that one comes in with a minus sign, the other with a plus sign. So when I add the effect of those two virtual photons together, I get 0. And of course, you would do that for every detuning, but every photon pair cancels. Okay, so that's destructive interference. Now, if we instead put these separated at 3/4 of a wavelength, then we still have the same story here, except there's constructive interference between the red and the blue detuned photons. Okay, and again, the detuning will take a pair that are equally detuned, 1 plus, 1 minus. But if we look at their coupling strength to the qubit, what you see is that, if you take this midpoint, one is coming in plus, there's a plus sign here, and the other comes in with a minus sign here, just due to where you are on the oscillation, right? And so as a result, now both of these contributions contribute with a positive sign, so constructive interference, and now every pair of photons will contribute to qubit-qubit coupling. Okay, so what I want to emphasize here is that depending on how far you put these qubits apart, you can either enhance or suppress the coupling between them, right? And that's as a function of wavelength, which is related to qubit frequency. And remember, we can tune the qubit frequency. So we actually have control and can tune this wavelength lambda. Okay. So at the end of the day, when you integrate over all of these virtual photon pairs, you find that the net coupling goes as the coupling of a qubit to the waveguide times the sign of the phase, where the phase is defined by the distance between the qubits. Okay, so that's a little bit of physics. Let's look at a device. So one experiment we did, we took what we call braided giant atoms. And so we took a qubit and we coupled it at 2 discrete points on a waveguide. And we took another qubit and coupled it at 2 discrete points on a waveguide. And we chose those points such that the distance between them was equal. And we'll call that distance phi for the phase. Okay. Now that phase, of course, is related to lambda. It's related to frequency. We can tune it. This is what the device looks like. We have an input. Here's the waveguide in blue that meanders around. It couples to qubit A, couples to qubit B, couples again to qubit A, couples again to qubit B, and goes to the output. We control the qubit frequency using the green lines, and then we can also read out the qubit using a conventional cavity QED readout. We did that so that we could read out the qubits in the cavity qubit or cavity QED way. We can also read out the qubits using the waveguide QED way. And so this was basically an experimental control for us. Okay, if we zoom in, this is what it looks like. The yellow part here is the capacitor to ground. Here's where we control the qubits using RF pulses, and here's where we control the qubit frequency, and then the waveguides in blue. So the first thing we're going to do is just focus on one qubit interacting with itself. This is a giant atom, and it has 2 connections to the waveguide. We're going to detune qubit B so far that it just doesn't matter in this experiment. And the phase that you see here, we'll call it 2 phi, because it goes from here to the other qubit. That was 1 phi, and then here's the second phi, so 2 phi distance. And that's related to the physical distance between the qubits, or between those 2 points, the velocity of a photon in this waveguide, roughly 1/3 the speed of light, and the frequency of the qubit. So again, we can tune this. And what we look for is dissipation. And what we see is that by tuning the qubit frequency or tuning this phase, we can go from a place where there's almost complete destructive interference to emit to the waveguide to something where we can emit to the waveguide. And so if we look at it in terms of qubit excitation in the excited state as a function of time, we get this decay function. And the longest lived one is about 30 microseconds. And that for this qubit is consistent with its non-radiative relaxation time. So it's not emitting to the waveguide, it's emitting to other defects that are nearby. And that's when we pick a particular frequency such that we have that this decay rate is minimized. So the decay rate is 1/T1, okay? So we minimize that when this is equal to -1, this goes to 0, and all we're left with is the non-radiative decay. But of course, we can then tune the qubit frequency, and as we tune it away from that point, we see that the decay time gets shorter and shorter, or decay rate gets larger and larger. Okay, so this is tuning the dissipation of the qubit from the waveguide. The important thing is that there's a decoherence-free point where the qubit does not emit to the waveguide because of the destructive quantum interference between these 2 points. You can think of it virtually emits to the waveguide, but then it destructively interferes, so it doesn't happen. Okay, all right, and that happens when 2 phi is equal to pi, right? Okay, and we can calibrate that. So now we're going to look at the waveguide mediated interaction with giant artificial atoms. So now we have 2 qubits, and we bring them close to each other in frequency or even on resonance. And as you'll remember, between these 2 points, the coupling between the qubits goes as gamma over 2 times sine phi. And that happens between every 2 points that qubit A is coupled to qubit B. And there are 3 of such points. But of course, there's also this long one, the outside coupling points, and they come in with 3 phi. So the net coupling between qubit A and qubit B goes as the sum of all of those contributions, right, for the constructive interference. And when we look at the qubit detuning and the probe field detuning as we try to drive a qubit, basically we're keeping one qubit at a constant frequency, and we're sweeping the other qubit in its frequency. And when those 2 qubits become degenerate, that's when they can swap energy with one another, and an avoided crossing opens up, as you'd expect. And the strength is 2g over 2 pi, or g over pi. And that's this coupling strength. You can see that it's several megahertz. So it's a fairly large coupling. So what's very interesting, though, is that we can do that. We can have coupling occur between these 2 qubits, right? But we could do it at a point where each qubit is in its own individual decoherence-free subspace, right? So that's really neat, right? The qubits are using the waveguide to talk to each other, but they don't emit any photons that cause them to decay to the environment, right? So we can have a finite coupling via the waveguide, but still engineer the dissipation of each individual qubit to be basically 0 to the waveguide. So decoherence-free interactions via the waveguide. Okay, so these are all building blocks. We can engineer the spectra in a couple of ways. So one is the number of coupling points that we have for each artificial atom. So if we have 2 and we look at the dissipation rate as a function of the separation between the points, it looks like this. But if we have instead 3 points, such as what's drawn here, we can get what looks like a double well type function for the decay rate. So now there are 2 decoherence-free subspace frequencies. Okay, and that continues. We could have 3 if we connected at 4 points, etc. We also know that the relative qubit waveguide coupling strengths matter. So if I couple at more than 1 point, I don't necessarily need to have them coupled with the same strength, right? So I could couple them, say, with one having twice the strength of the other, or 1.5, or even more. And what you see happens there is that flattens out this barrier, if you want to think of it that way, but you're increasing the range of the decoherence-free subspace doing that. Okay, so that's another knob that we have to tune. And of course, we already talked about that the distance between the points, or our qubit frequency, is the third knob we have. So there's lots of engineering that can be done here. So let's take a look at an example of n equals 3 connections per qubit. So qubits connected at 3 points on the waveguide. There are 2 qubits, and now the phases are not all identical, or the separations are not all identical. This is what it looks like. Again, this blue meandering waveguide goes from the left side to the right side of the chip, and it now couples to each qubit 3 times, right? And this is the zoom in. You can see the 3 points that it couples to on this qubit. Whoop. To give some numbers, we've chosen the distances such that 2 of these phases are half of the other phase, phase 2. All right, and the coupling strengths are also different, as you can see here. So this is what it looks like when we map this out. So what we're doing is looking at the decay rate as a function of, say, a qubit frequency, and you can see that it has this double well profile because we coupled at 3 points, so we get 2 decoherence-free points, right? And we can also look at the coupling between the qubits, which only happens when the qubits are resonant, right? And you can see that the coupling strength is non-zero at each of the decoherence-free subspaces, and which is what we would desire. Good. So with that, we can perform coherent operations with qubits while they're coupled to a waveguide. And here's what that looks like. So we start with 2 qubits. Qubit A is in one of these decoherence-free frequencies. The other is put at the other decoherence-free frequency. So they're each one is protected from the environment, but they're non-resonant, so they don't talk to each other, right? Okay, so the first thing we do is we'll put qubit B in its excited state. We'll then shift the frequency of qubit A and bring it onto resonance with the qubit B. So now they can swap. They perform a swap operation with each other. And then we do readout, or sorry, then we detune them again. We put them back in their protected spots and we do readout, okay? And when they're resonant with one another, there's a swap operation that happens. And so when they're perfectly resonant, so there's 0 detuning, you can see that what's yellow here is blue here and vice versa, indicating that the excitation that we had in qubit B is now swapping back and forth with qubit A. That's what we want, okay? This is what it looks like. If we take a slice along the detuning equals 0, and so each one oscillates, you know, now qubit A has the excitation and qubit B doesn't, and they swap and they swap and they swap. But what we'll do is we'll pick this time right here, right, for the duration of the interaction, because that's going to create an entangled state. And it creates this state in particular, 0, 1 minus I, 1, 0. This is why it's called an I swap. And if we do qubit state tomography to confirm that we did make this state, we do that with a fidelity, we show that it's a fidelity of 94%. Okay, and that was this one of these papers where we demonstrated this. And so we can entangle qubits despite the fact that they're coupled to an open environment. And this is remarkable. I mean, in the past, people wouldn't even quote fidelities for qubits coupled to waveguides because they relax almost instantaneously. Like they relax so quickly, it's hard to even do this pi pulse without the qubit, you know, relaxing, right? So due to the giant atoms and the destructive interference, we can get this 94% fidelity. Okay, let me now talk about directional photon emission, and it's a story about quantum interconnects, which is where we started. You know, we think that networks enable modular and extensible quantum computation because we want to build nodes that work, and then we need to entangle those nodes, and we need quantum interconnects to do that. And there have been some demonstrations of this so far, but they all come with some pros and cons. And so one way is to do this by coupling via a cavity. So you have 2 qubits coupled to a cavity. This to date is given the highest fidelities, and it is bidirectional. You can, send a photon from qubit 1 to qubit 2 or back, but it's limited in the node connectivity. Like how many qubits can I really couple to this waveguide? And it also is limited in distance because as I make this cavity, sorry, I called it a waveguide, it's a cavity. As I make the cavity longer and longer, the resonance frequencies of that cavity get closer and closer together. So that's a problem. The second way that's been done is to couple via a single-ended waveguide with single photons. And so you have a qubit that can couple to a waveguide. The photon can go in one direction to qubit 2, but it can't go the other direction because it requires this non-reciprocal component with a 50 ohm termination. And these tend to be quite lossy. So the fidelities here aren't that high. And so you'd like to take the pros of both of these and throw out, the cons. And so we've developed a concept, and actually it was proposed by Gerhard et al. And we're starting to demonstrate it, a modular quantum interconnect using bidirectional photons. And you can do it by coupling modules to a waveguide and then sending a photon between them. So it requires being able to choose the direction you emit a photon and being able to receive it. So the platform, of course, is our artificial atoms on a 1D waveguide. And these superconducting qubits emit, but they emit in both directions. And we need to come up with a way to be able to choose which direction that it's going to emit. All right. And as you might imagine, it's going to involve putting 2 qubits on this waveguide and leveraging the quantum interference so that we control their spontaneous emission direction. Okay. So this is what it looks like. We've got 2 qubits, each one with a frequency omega. We can put them into an entangled state of this form, and this phase becomes important. So one is excited, so EG plus e to the I pi over 2 GE. E and G are excited in ground state. And we couple them to a waveguide, and they're separated by a distance, we'll call it x. And so we have e to the plus or minus ikx representing that separation, where x is lambda over 4 separation. And basically, when we put that entangled state into these qubits, it emits very quickly to the waveguide. And when it does so, here's what happens. There are 4 cases that we're going to look at. So in one case, it was qubit 1 that was excited. So it's this term of the superposition right here. And it's going to emit at x equals 0, and it emits to the right. And when it does that, it comes in with these 2 phases. So one is the qubit state phase. So there's, basically 0 phase here, e to the I 0. And the other is the position phase. And so the position is x equals 0. So that one's also 0. And that's what it is. Now, the other case is that qubit 2 was in the excited state and it emits. And so now its state phase is e to the I pi over 2. And its position phase is also pi over 2. Comes in with a minus sign, by the sign convention we've chosen. But it's pi over 2 away because it's separated by lambda over 4. Okay, so that's the second case. Now, the third and the fourth cases are the same, but the photon is emitted to the left. And so what that does is it changes the minus sign of the position phase to plus sign. And what you see is that these 2 destructively interfere, and we're only left with photons that propagate to the right. Now, there's one detail. Okay, and we would write that this way. We would say that the state of the photons in the waveguide are 0, 1, where 0 left, 1 to the right. There's a detail that we've overlooked. You might be thinking, what about the coupling between these 2 qubits via the waveguide? That's still there. And so what we need to do is counter it by putting direct coupling between qubits 1 and qubit 2 and making it exactly the opposite strength so that those couplings cancel out. And the only thing we have left is this constructive or destructive interference due to the state of the qubit and their separation. Now, the same thing happens in the opposite direction. I won't walk through it, but if we change the sign of this phase to minus sign, now the photons that get emitted go to the left, and our state is 1, 0 instead of 0, 1, and the other ones destructively interfere. So just by choosing the state of the entangled state, we can affect the direction of the emission. So this is what our emitter module looks like. We have the 2 qubits that are going to emit to the waveguide. And we have 2 qubits that we can imagine are part of a processor or a module, qubit 3 and 4. And those are coupled together. And then the idea is that we create an entangled state between 3 and 4, and then we shuttle it down to 1 and 2 via couplers 1, 3 and coupler 2, 4. So this is what the device looks like. You have qubits 3 and 4 with their coupler. you have qubits 1 and 2 with their coupler. Here's the waveguide in magenta. And then you have these couplers on the left and the right, which are going to take the module's entangled state and then shift it down or shuttle it down to the waveguide qubits that emit to the waveguide almost instantaneously. Okay. Now, the way we do this is we start with an X pulse on qubit 3. We could do it on qubit 4, but we do it on qubit 3. And then we drive the coupler. This is a tunable coupler. I didn't talk about how it works, but we drive that coupler, which creates an interaction between qubits 3 and 4. That's an I-swap gate. And then what we do is now we've created an entangled state. And with these couplers, we shift that entangled state down to qubits 1 and 2. And that's when they're released. Okay. And so whether it goes left or right, again, depends on the phase we've chosen for qubits 3 and 4. That entangled state. And so if we choose it to be one of those entangled states, the plus sign, let's say, then we get emission to the right. And if we choose it to be negative, then we get emission to the left. And what we're measuring here is amplitude. And so you may remember that we can't measure in this basis a Fox state. So we basically create a superposition state that allows us to measure the amplitude. Now, when we measure power, we don't need to do this, but when we measure amplitude, we do. And that's why we can see the amplitude of the photon field that's emitted either to the right or to the left. And when we do this, we do the same integration of the signal that we talked about before with a windowing function here. It's not shown. And we're basically measuring the ensemble average of destruction operator to the left or to the right. So we can do state tomography of the photons that get emitted from this waveguide. And what you can see is any photons that go to the left basically are 0. And any that go to the right, you can now see that A dagger A, which is the number operator, has the highest response. And then the correlations between left and right are very small. Same thing if we send the photon to the left, same story. And when we look at this in terms of the skyscraper plot of all different possible combinations, we find that the fidelities here we're generating directional photons with 97 to 98% fidelity. Okay. So what's interesting about this module is it works in both directions. You can use it to emit a photon, but you can also use it to absorb a photon. And I won't show the absorption. We're working on that experiment right now. But the way we imagine using this is that you have module quantum processing units, right? And we want to connect those modules together. Well, what we do is we use this emitter receiver module, let's say. And so what we can do is set them up. They're all coupled to waveguides, but we can bring these modules onto resonance when we want to emit a photon, for example. So we emit a photon from here, and it will travel. It'll bypass this one. It bypasses this one because they're detuned. But when it gets to this one, these are resonant. And basically, just by doing the time reversal of what we did to emit the photon, we can bring it back in up to the top of the module, and then we can interact it with this module's QPU. So that's the vision of where we want to go with this. I think I'm coming to the end of the hour, so let me just quickly show you a few slides on 3D integration, if that's all right. We talked earlier, I showed this picture of 5 qubits in a linear chain, and of course that's interesting, and we can do interesting experiments with that with high fidelities. But we also want to do 2-qubit or 2D arrays of qubits, and so this is a 16-qubit chip that we've got. But you immediately see that it's getting quite crowded. There's a lot of biasing and readout wiring around the outside, and in fact, in this case, we had to bring in some wire bonds to reach and control these inner 4 qubits, right? And of course, we know that this is not extensible, right? If we went to 5x5 or 6x6 array, this is just not practical. So this motivates the need to go to 3D integration. Before I get there, let me show you some experiments, though, that we did with a device. In this case, it's a 3x3 array. And you can think of Manhattan distance as counting the number of steps you would take as if you were in Manhattan. It's a grid, right? So 1, 2, 3 steps, for example. And you can get to the other side in 4 steps. So one step, that's this line. This line is 2 steps away from the lower left, 3 steps away, and 4 steps away. And so if you look at the number of steps away as a function of the evolution time by putting an excitation in this lower left corner and then saying go, you can see that it oscillates back and forth. It goes to the upper right, back to the lower left, to the upper right, to the lower left. This is the experiment. This is the simulation on the right. Okay. And what we're modeling here is a Bose-Hubbard Hamiltonian. I'll just show the Hamiltonian here. It has local site energies, meaning we can tune each qubit. It has on-site interaction, which is basically what we call qubit anharmonicity. And it's the difference between the 1-2 transition and the 0-1 transition. So if I put a second excitation on the qubit, what energy difference do I get? And then there's the interaction between the qubits because they are capacitively coupled to each other. And now in this case, it's called hardcore limit because the U is much greater than J. Okay, so we observe a quadratic speedup of this lattice propagation in 2D. That's what we expect. And we've also done some experiments in localization. So one type of localization that you're probably familiar with is called Anderson localization, and that can be in 1 dimension or in 2 dimensions. And what we do is we just detune our qubits randomly from one another. So their energies are not the same, but slightly different. And the degree to which they're different is a parameter, which we call disorder strength. And we'll call it delta, and we'll just normalize it by J because that's a common thing to do. And what we're plotting here on the left is basically a notion of what we call participation ratio. But what it models is, how localized the excitation is. And so when the disorder strength is very strong, it's highly localized. And when it's weak, it's delocalized. And so you can start with an excitation here in the upper left, and then we'll turn the qubits on in such a way that these guys don't participate. And then you can ask, how does the excitation progress? And we can do it also in 2D, and we get good agreement with both simulation of the qubit array we have, as well as the theory of the Bose-Hubbard model. There's another type of disorder called Wannier-Stark, where you basically disorder the qubits, but you do it in a way that there's a gradient in some direction. And that can be in 1 dimension, or it can be in 2 dimension. Here it's shown in 1 dimension. And we put an excitation on qubit 2, and then we ask, how does that spread? And it tries to spread in both directions. Please forgive this arrow. It actually tries to go to both 3 and 1, and et cetera. But because of the gradient, it actually comes back, and then it does it again and again and again. And these are, in fact, called block oscillations. And you can see again that this, as a function of the slope of this potential, matches pretty well. We can do it in 2 dimensions. And now there's 2 gradients. There is a gradient along the x direction and the y direction. And I'll just say that, this again matches the theory pretty well. And if you'd like to see more about this work, you can find these references here. They've since been published. But they're still on the archive. So we have these 2D array of qubits, and through a very generous donation from Keysight, we're building a quantum test bed that's capable of measuring up to 64, so up to 8x8 array of qubits. But we know in order to go in that direction, we need 3D integration. And so we've been doing a lot of work over the last 5 to 10 years. And what we've been doing is basically creating what we call a 3-stack. 3-stack has 3 chips. The qubit chip is on top. It's actually face down. There's an interposer, and the interposer has through silicon vias in it. These are superconducting. And then at the bottom is what we call a readout and interconnect chip. And in our case, this is superconducting. You can think of it as a multi-layer printed circuit board, but in our case, it's a superconducting multi-layer, multi-wiring layer process that we have. And so basically the idea is your signals can go over and under each other very easily in this lower readout and interconnect layer. When they get to the right spot to address the qubit you want to address, the signal comes up through the TSV, addresses the qubit, and then of course a readout signal comes back. So that's why it's called readout and interconnect. Now, there's some features of this, and one is that the reason we do this in this way is that the qubits are very sensitive to their environment. We spent a long time, groups worldwide have spent a long time trying to optimize how we can get a high coherence time. And part of it is based on this substrate and not having lossy dielectrics nearby. So by putting an interposer that uses the same type of silicon in processing, we haven't really changed the story. The qubits, say, electric field on this capacitor still sees basically the same environment. So the qubits have high coherence. Doing this allows us another plane that we can put active elements on, whether they're qubits or tunable couplers. The through silicon vias are very important, and these are superconducting through silicon vias. That was an innovation that we did. And then, of course, this bottom layer is something we've been working on for a long time. I'll just show some pictures. The top layer is the chip, but it's flipped over face down. The through silicon vias look like this. It's about 10 or 20 to 1 aspect ratio. So 10, 20 microns up here, but 200 microns deep. It does superconduct, and it superconducts below about 2.5 Kelvin. This is made from titanium nitride. And then this multi-wiring layer process, you can see here 8 wiring layers. These are niobium, has junctions, has resistors. This is actually used for classical digital technology called SFQ. We also use it for traveling wave parametric amplifiers and other uses. But in this context, it allows us to route wire signals where they need to go through these vias. Now, these vias are very small. The distance between here is maybe 150 nanometers, right? Or here it's shown between 150 and 200 nanometers. Okay. So with that, let me conclude. I appreciate your patience. I know I went over by 2 minutes, but let me acknowledge quickly the folks at MIT Lincoln Lab. This is not a picture of everybody. I think it was everybody that could show up for the picture. It's a very large team, as well as the team at the Engineering Quantum Systems Group, also a very large team. And of course, all of our sponsors who make this work possible. And thank you for your attention. Really appreciate this opportunity.
Thank you so much for an excellent talk. I really found that interesting. I guess we could go around and take a few questions. We could start on Zoom, if that's easier. Are there any questions on Zoom?
Sure, I have several questions.
Okay, go ahead.
Thank you very much for the talk. It was great.
Oh, thanks. Yeah.
One question I have, actually from the very beginning, when you were talking about the frequency ranges for your Josephson junctions, definitely, the hardware is much better down at 5 gigahertz or 10 gigahertz, around X band is radar, of course. I'm curious if there are other reasons why people don't go to higher frequencies. Are there, I sort of have alternative reasons why I think it could be interesting to make higher frequency transmons or Josephson junctions, but I guess my question is, are there coherence issues, or is there more noise at higher frequencies?
Yeah, no, that's a great question. People have been thinking about it, and I think it's a good idea. The one advantage is, of course, that your thermal, what sets the temperature of the environment is that frequency. And so if you can go to higher frequencies, you can handle higher temperatures. Now, it is true that if you look at, a simple model of what the mode, the continuum of modes is in an environment, then things do get worse as you go to higher frequencies. And so that's one issue, is that there is the potential for, enhanced spontaneous emission at those higher frequencies. But, those models are pretty generic. And I think, through engineering, just like with cavity QED, maybe we can come up with something that protects the qubit up there. Another reason, or something to think about, is, the Josephson plasma frequency. And so for, aluminum, we're up around 100 gigahertz or so. And so you're not going to go above that with aluminum. And in fact, probably you would be shy of that for sure, just from practical considerations. You could switch to other superconductors like niobium, which would be up around 700 or 800 gigahertz. But niobium, we made a lot of qubits out of niobium, around 2005 to 10 timeframe. But for a number of reasons, mostly lots of having, oxides in niobium, it's very lossy. And so even though you might be gaining some advantage in the temperature, you pay a huge penalty, at least as we know how to fabricate it today. Now that's not a no-go criteria. It just means people have spent a lot more time optimizing aluminum than we did optimizing niobium. So, and there are other materials like tantalum that are hot now. So I think that there's a pathway there and people should study it. I should also mention that there's the other direction to go, which is to lower frequency. And we have qubits that are down at 100 megahertz or even 50 megahertz. And at a first blush, that might seem like a bad idea because now you're even in a dilution refrigerator, you're going to excite that qubit. But that excitation rate through the Boltzmann relation is basically related to T1, down and up, right? And the advantage you gain for some qubits is that the T1 can be millisecond time frame. So if you can initialize the qubit in its ground state, even in a hot environment, it will stay there on the order of half a millisecond or a millisecond. So there are reasons to think about both directions in frequency. There's nothing magic about 5 gigahertz.
Yeah. I'm curious, what is the typical T1 scaling with frequency?
I think it depends on the dimension of the system, but it'll either be omega or omega cubed, something like that.
Okay.
Yeah. And then in terms of, if you think of Fermi's golden rule, that's for the environment. But if you think of Fermi's golden rule, then the decay rate goes as basically the coupling between, the 0 and 1 matrix element, that squared. And so it's that times your environmental frequency dependence.
All right. Thank you.
Yeah, thank you for the question.
Are there any in-person questions for Professor Oliver? Okay, if not, I have a question actually. This goes back to, I guess, like the middle part of your presentation, talking about the, coupling artificial atoms to the waveguide structure. You reported a 94% fidelity for coupling, or basically producing an entangled state between 2 artificial atoms using a swap operation. If you wanted to extend that to multiple, I guess, like, if you wanted to extend that to having multiple and arbitrary interacting artificial atoms, would you have to perform multiple swap operations since it's only limited to nearest neighbor coupling? And also, like, how do you expect the fidelity to scale with the number of qubits that you add, or the number of odd atoms?
So in that experiment, we had qubits A and B, and they were talking to each other via the waveguide, right? So one nice feature of this is that it doesn't have to be nearest neighbor interaction. It can be non-local, right? So of course it's a one-dimensional waveguide, so you can have non-local coupling in one dimension. Now, you could think about ways of wrapping waveguides over each other, or same waveguide, but it crosses itself, without shorting, using 3D integration. And now you could, in fact, couple arbitrarily qubits in a 2-dimensional array. And what it requires is that you bring qubits on resonance and off resonance with one another. That's basically what needs to happen. But there's a lot of engineering and choosing the positions and things like that. But that's certainly possible, and it's one of the advantages of trying to do this via waveguide is that we're no longer limited to this as fabricated nearest neighbor interaction where things are now fixed on the chip. That you can have a non-local coupling between qubits that are, in principle arbitrarily far away. I'm sure in practice there's going to be some limit, but it's not limited to nearest neighbor interactions, is what I wanted to say. And in terms of how the fidelity will scale, that's a good question. I think one requirement is, of course, that we can still like the propagation of the photon, it basically looks instantaneous, and we're in this basically static regime. And I think that's true for certainly the size chips we're working with today, and probably will be for the foreseeable future. But that is, there are boundary conditions that, and essentially there are some assumptions that we've made that are very reasonable now that we want to keep in mind as we go to larger and larger systems.
Right. Yeah, that makes a lot of sense. Thank you.
Yep.
Are there any other questions? Yeah, Amrita. Yeah, the question was, if you have qubits connected to 3 points in the waveguide, is there a reason why the separation between the qubits is not the same?
I'm sorry, is there a reason why
the separation between the qubits sitting along the waveguide is not the same?
Yeah, because the I think if I understand the question correctly, is that by choosing the distance between those connection points, remember that was one of the knobs that we could use to choose the decoherence-free frequencies, how many there are, and then also how they interact, how the qubits interact with one another, the interaction strength. So it's all part of, there's no right answer there. I think it's about having a goal in mind of what you want to achieve, and then these are the knobs you've got that you can tune to achieve that goal.
That makes sense. Anything else? Okay, if not, we could give one last thanks to Professor Oliver.
Yeah, and thank you very much. I really enjoyed it, and I hope you did too.
I really did. Thank you so much.
Yeah, thank you.
All right.
Yeah, thank you so much.
And next week we'll have Sinead Griffin from Lawrence Berkeley Lab. That'll be completely virtual, talking about quantum materials. Anyways, thank you all.
Yeah, thanks again, Nima. Really enjoyed it.
Yeah, definitely. All right.
Yeah, keep in touch. See ya.
Yeah, definitely. Bye.